All right. So in chapter 13, one of our key applications was to find the flux. So recall we have some surface in three-dimensional space, and we have a vector field. It could be like a velocity field or a wind field, but a vector field, and the vectors move in a certain direction. And we want to know if the net rate of flow of the vector field is inward, going overall inward to the surface, or outward from the surface. And this is relative to a positive orientation on the surface, where like if the net rate of flow is outward from the surface, that would represent positive flux. And if the net rate of flow is inward to the surface, that would represent negative flux. In other words, positive flux means you get a positive value. Negative flux means you get a negative value. And of course, we did an example when we first learned about flux, where we had a closed, well, we had two surfaces. Okay, we had two surfaces. One, let me just see here. One was a paraboloid, and the other was a disk. I don't know if you remember this. We had a surface. Okay, let me just see here. One moment. Let me just double check here my notes on this. I want to make sure I'm referring to the right example. Okay, so I believe, yeah, we had, hold on class, one moment. Yeah, it wasn't exactly this, but I'm trying to, so we had, hold on here. Let's do this right. Okay, so this is X, Y, and hold on, Z. And if you recall, we had a paraboloid come out from the origin there along the y-axis. Okay. And it stopped at y equals 1. And so we had a surface S1 and a surface S2. And we had a vector field present in the, in the three-dimensional space. Okay, and we wanted to, and our surface S was equal to the sum or the union of surface 1 with surface 2. And if you recall, when we wanted to find the flux here, hold on one moment. Yeah, we wanted to find the flux across the entire closed surface. Well, we had to find the flux across surface 1. and add that to the flux across surface 2. Okay. And this was when this was from section 13.6. How many recall that? How many recall that example? How many remember it? Robin remembers it. Eric remembers it. All right, and so, you know, essentially, this surface S, okay, this surface S here was a closed surface because it enveloped a solid. It enveloped a solid E completely. The solid E was completely encased by this surface S. But in order to find the flux across this surface S that completely, hold on, I want to say it the right way. In order to find the flux across this surface S that was the boundary of that solid E, we needed to add 2 flux integrals. Well, with this divergence theorem, section 13.8, there's a special theorem that will allow us to compute the flux across a closed surface like that without having to add 2 flux integrals. Okay, so that's what we're going to learn today. Are there any questions? Okay. Well then, let me go back to the ebook here. So, divergence theorem. Okay, divergence theorem. You learned about divergence, right? You learned about divergence in, let me see, that was in section, trying to keep my classes straight here. I believe it was section 13.5, right? Okay, well, with the divergence theorem, what we're going to do is, if we have a situation, okay, if we have, and I'll highlight this whole thing here, if we have a situation where we have a solid region, E, or a solid, and you have S as a boundary surface of E with positive outward orientation, okay, then, and if we have a vector field whose component functions have continuous partial derivatives on an open region that contains E, then the flux across the entire surface can be, well, it will equal the triple integral of the divergence of F. Okay, divergence of F, right? The divergence of a vector field is going to be a function, right? A function. So we're going to integrate that function across this solid E. So the divergence theorem, they mentioned it's sometimes called Gauss's theorem after the mathematician Carl Friedrich Gauss. He lived from 1777 to 1855. He lived to be 78 years old, which is pretty good back then. And he discovered this theorem during his investigation of electrostatics. Okay, so the theorem, they prove it, but the proof is quite difficult. The proof is quite difficult. But you are certainly welcome to look at the proof if you want. I'm going to be holding, you know, even though next week is final exams week, I am going to be holding office hours if you want, I can go over the proof with you at office hours if you like. That's not a problem. I mean, I see the proof here. It's it really has a lot of different elements to it. But I think what I'd like to do, I mean, come see me if you want to discuss the proof. Not a problem. I think I'd like to go, right to a few examples here so that I can, let you get started working on your new assignment here. All right. Are there any questions before we move forward here? Okay. Okay. So, all right. Well, let me move forward here then. Okay. So, and remember. Okay. So we'll here's example one. Here's example one. Let me just highlight it here. So what we want to do is we want to find the flux of the vector field over the unit sphere given by x squared plus y squared plus z squared equals 1. So what we do is we compute the divergence of the vector field f. We compute its divergence, and that turns out to equal 1. And the unit sphere is the boundary of this bowl that's inside. And so the divergence theorem will help you compute the flux across this surface, this sphere. And it turns out that, well, in this case, oddly enough, in this case, since the since the divergence of the vector field equals 1, the actually finding the flux is equivalent to finding the volume of the ball of this sphere of radius 1, because in the triple integral there you have a 1 in the triple integral over this ball B, you have a 1 and then a dV. Well, that just stands for volume, right? So you get 4 pi over 3. Okay, are there any questions on that? Okay, it's pretty. How many like this theorem? How many really like this theorem? Okay, all right. John likes it, and Eric and Robin and Ryan. It is much easier, but all right. Eric likes it, but let me ask you this. Let's say that you have. Let's say you have this paraboloid. Okay, centered at the origin. And here's your surface S. But the surface S does it doesn't include the bottom. Okay, so in other words, think of this. Let me write it another way. Hold on. Let me do it this way. Hold on. Okay, so this is a paraboloid. Here's your surface S. Here's the origin. But the surface is just the surface S. Okay, and you want to find, so it does not include the disk at the bottom. Okay, so this is not included. Bottom disk. Bottom disk. Hold on. Sometimes it works better with the mouse, sometimes not. Bottom disk, not included. Okay, would it be true then, would it be true in this case that the flux here, would it equal the triple integral over the solid E? So we know that we know the solid E is the parabola, right? Would it equal, in this case, would the flux equal this triple integral? Can we use the divergence theorem in this case, where our surface S is just the open paraboloid? It does not include the bottom disk. So it's an open surface. The surface is not, it's not closed. It's open on the bottom. That's right, Robin. You cannot use the divergence theorem. The divergence theorem is only true when for closed surfaces. And so what you'd have to do to find the flux for this type of for this surface, this open surface, you'd have to use what you learned in section 13.6. Okay, are there any questions on that? The reason I mention this is students tend to think they can apply it all the time, and you cannot. You cannot, and you have to be aware. You have to be, very aware of that. The final exam, you're going to be tested on these kind of things. Chapter 13 is important for the final exam, and so. Okay, great. Well, then let me go ahead and go back to our book here. Okay, so they have a nice example, example 2, where they talk about a surface integral that's much easier with the divergence theorem. Okay, so what they want you to do is they want you to compute the flux across a surface, okay, where the vector field is given there, the vector field F, and the surface S. The surface S, maybe I can highlight it here. The surface S is the region. Is the region E, although I like to call it solid E. It's let me get it just a little bit lower. This is your surface. The surface is, well, it has the parabolic cylinder z equals 1 minus x squared. Okay, and then it gets that, it cut the plane y plus c equals 2 cuts that cylinder along that angle there on the right, that plane on the right, and then it's bounded below by the xc plane, and it's bounded on the left by, no, it's bounded below by the xy plane, and it's bounded on the left by the xc plane. Okay, so if we wanted to compute the flux, okay, for this the flux across this surface, and let's say it's a closed surface, so we could use the divergence theorem, right? We could completely closed surface, but if we were to decide, hey, let's not use the divergence theorem, how many flux integrals would we need to compute? How many flux integrals would we need to compute and add? All right, I love it when we get different answers. Thank you for everybody. It's actually, you're all, well, the answer is 4. The answer is 4. So you have on top, you have the cylinder there on the top. And then on the right side, you have that plane, okay, that's cut out, that cuts into the cylinder. That's side 2. You're bounded below by the xy plane, that's side 3. And then you're bounded in the back on the left, on the left by the xc plane. Ah, okay, Eric. Yeah, yeah. So, how would, what do you want to do? Do you want to find the flux for each surface and add 4 flux integrals, or do you want to use the divergence theorem? What's more appealing to you? It's kind of an obvious question, but divergence theorem. Okay, all right. Well, let's continue then. Let's continue. So they mention here that it would be extremely difficult to evaluate the given surface integral directly because you'd have to evaluate 4 surface integrals. I mean, you could do it. I don't know if extremely difficult is the right word, but it would be more difficult. Also remember, you would have 4 double integrals to compute too. But if we use the divergence theorem, we take the divergence of that vector field, which they have done, and they get up, you end up getting 3 times y. Okay, and so now, of course, we have the divergence. It equals 3 times y. Okay, and that's fine. That's fine. But now, the one thing we have to get, of course, are limits. We have to get our limits for this triple integral. So I want you to take a moment. Well, let me ask you this. Should we use rectangular coordinates? So I'm talking now the triple integral, okay, for the divergence theorem. We have to find limits. Should we use rectangular coordinates, cylindrical coordinates, or spherical coordinates? What do you think might be good? Let me ask you this: would spherical coordinates be good? Yes, spherical. That's right, That's right, Jamal. That's right, Eric. Spherical will not work well. And I actually agree with Ryan. Rectangular is probably the best way to go here. Okay, so okay, well then now that we've you know, if we want to use rectangular coordinates, well, we have 6 different possibilities, right? You could do dz, dy, dx. You could do dz, dx, dy. You could do dy, dz, dx. You could do dy, dx, dz. You could do dx, dz, dy, or hold on, dx, dz, dy, or dx, dy, dz. You have six orders. So, you know, we really have to think about how we want to do it. Could we use dy, dz, dx? Could we do dy, dz, dx? Here's, I guess, what I'm asking. Here's what I'm asking. Okay. Let's say the book chooses to do um hold on here. The book chooses to do dy, dz, dx. Okay, the book chooses to do that. Could you, and go ahead and write that down. Go ahead and write that down. Okay, and then going back to the solid here, what would, and actually let me write it down too. Think about what the, you know, see, just take a few moments to try to figure out your limits. Okay, if you're going to do dy, dz, dx. Okay, let me give you a few moments to try to think about what those limits are, and then we'll talk about the solution, okay? Okay, hold on here. I see something in the chat. All right, so let's see here. All right, Ryan, I'm looking here. I'm looking at what you're suggesting here. The y is correct. Y goes from the plane y equals 0 to the plane y equals 2 minus z. Okay. So I like your thing, Ryan. let me just, you're right. Don't look at Ryan's answer in the chat window, everybody. Spend a little more time. But you're right, Ryan. And then we'll, very good, very good. Let me just give you all another minute. Okay. Okay. So let's go ahead and then show the limits here. Okay, so who got those limits? Y goes from the planes y equals 0 to y equals 2 minus z. And then if you project that solid into the xc plane, you'll get a half of a circle. It goes from z equals 0 to z equals 1 minus x squared, and then x goes from -1 to 1. Okay, very good, Eric. Very good, Robin. Very good, Diodath. I hope I gave everybody, did I give you all enough time? I hope I did. Sorry if I went a little fast. I was, but hopefully, you know, very good, very good, very good. Okay, so are there any questions on that? Okay, well then the flux in this case is going to equal 184 over 35. Okay, are there any questions on that? Who's feeling good? Who's feeling reasonably good? Good, Ryan. Excellent, Robin. Very good, Eric. Okay, good, John, good, Eric. Then Dan's feeling good. Well, let's move forward then. All right. So, okay, then, so the book actually talks, it talks about divergence in relation to, there's some nice applications, flux, electric flux, and so forth. So feel free to, those of you taking physics, you're welcome to look that over. So let's see here. Something else I wanted to point out here is how many of you have heard of, let me see here, hold on. How many have heard the term, now let me just see, one moment, class. How many have heard the term sources and sinks? That's sometimes a common term. I mean, it comes up. What they do in figure 4 is they show you a vector field. Okay. And they comment that, I want to make sure this whole thing shows. Yeah, it appears, well, I got to make the whole thing, I might have to make it a little smaller. So they say, let me bring it down just a notch here. No, got to take it up one. It appears that vectors that end near P1 are shorter than vectors that start near P1. Okay, if you look at the point P1, the vectors, I'm going to say this the right way, the vectors coming into P1 are getting smaller. Okay, they're getting smaller. Okay, than the vectors that start near P1, that come, like, if you look past P1, the vectors get bigger. All right, so what's the net flow? Okay, the net flow outward. Well, is the net flow at P1 outward or inward? If you think about vectors flowing into P1 and then vectors flowing out of P1, and think about the size of the vectors, is the overall net flow positive or negative? And maybe I'll make this a little bigger so I can. That's right, Ryan. That's right, Robin. It's positive. So the net flow at P1 is positive because the vectors flowing, like, away from P1 are larger in magnitude than the vectors flowing into P1. Okay, and so there we say the divergence is greater than 0. So an outward divergence means, well, if divergence is positive at a point, it means net flow is outward. Okay, net flows outward. But on the other hand, if you look at the point P2, okay, for that point, okay, think about the vectors flowing, like, in towards P2, and then the vectors flowing out from P2. Is the net flow inward or outward? The net flows inward. That's right, Eric. That's right. And so in that case, would the divergence be positive or negative if the net flows inward? What's your intuition tell you? It would be negative. And, you know, I just wanted you to be aware of this kind of thinking, because you're going to have one problem in your homework on it. And, you know, if it comes up on the final exam, I just want you to feel comfortable should a problem like this occur on the final. Are there any questions? Okay. Okay. Well, let me stop the recording then.